Okay, so in this video, we'll just be continuing our discussion from the previous video in which we examined the effects of surface tension in a capillary tube. Previously, we looked at liquids with contact angles less than 90 degrees, so for example, water and glass, in which the liquid rises relative to the free ambient surface. Now, we'll look at liquids with contact angles greater than 90 degrees, so for example, heavy metals and glass, in which the liquid falls relative to the free ambient surface. We won't go into as much detail in this video regarding the mechanics and explanations of the meniscus, so if you're interested in the details of that analysis, please watch the previous video. So to begin, let's review our assumptions. So assumption 1, we're going to deal with an air-liquid interface. 2, we're going to deal with an isothermal incompressible system. 3, we're going to deal with a constant gravitational field. 4, we're going to deal with a static system. 5, we're going to deal with gravity as the only body force. And 6, we're going to assume that all surface tension effects occur along the curved meniscus within the tube. And we kind of reviewed that assumption in the previous video. So the goal here is to find a formula to predict H, or the displacement of the liquid level surface within the capillary tube relative to the free ambient surface. Here we show H defined as this displacement from the free ambient surface all the way down to the free liquid surface within the capillary tube. And big H is defined as the distance from the bottom of the capillary tube to the free liquid surface within the capillary tube. And then in the diagram below, we just show how the definition of the contact angle remains the same as it did from the previous video. It's just the angle between the curvature of the meniscus and the capillary tube wall. Here you can see theta, or that contact angle, is greater than 90 degrees in this case. And we would see this, as I mentioned, with a heavy metal and glass like mercury or something of that sort. So again, the formula to find H is the goal here, and we will begin that on the next slide. So we're going to kind of follow the same algorithm here. We're going to do a free body diagram in Z for the liquid in the capillary tube, and we have the standard forces from the previous video. We have our atmospheric pressure distribution above the meniscus. We have our hydrostatic pressure distribution below the meniscus. We have our surface tension forces that are isolated to just the meniscus of the liquid in the capillary tube. And we're using the same simplified geometric assumption where we are using the 2D projected area of the meniscus as the area over which the atmospheric pressure distribution acts to simplify the analysis and not need to use a double integral. Here we have gravity acting down, and we have Z as positive up, as is necessary for hydrostatics problems. We have our little h, which is the displacement from this free ambient surface to the liquid surface in the capillary tube, and our big H, which is the distance from the bottom of the capillary tube to the free liquid surface in the capillary tube. Now we're just going to be breaking down our surface tension, and again, our surface tension is essentially a vector that is normalized by a scalar, which is itself a vector, so you are able to decompose it into components. Again, the units of surface tension are newtons per meter. You can kind of treat it like a vector in that sense. It does have a direction, it does have a magnitude. So what we end up seeing here is if we map our theta, our contact angle, to the triangle that we use to decompose our surface tension, our theta maps to this theta right here. And when we draw our triangle around our sigma, just like this, we see that the angle we're going to use to decompose our sigma, our surface tension, is this angle right here, which we're going to call psi, and it is actually equal to 180 degrees minus theta. It is not equal to theta. It is equal to 180 degrees minus theta. That will be important later on in the video. So for now, we're going to operate with psi, keeping in mind that it is equal to 180 degrees minus theta. That is just a result of the geometry of mapping this theta right here, the contact angle, to the angle we need to decompose the surface tension. So with that being said, we have our expression for the surface tension in X and the surface tension in Z, both of which are magnitudes. The surface tension in X is equal to sine psi times sigma. The surface tension in Z is equal to cosine psi times sigma. So now we're in the same spot that we were in the previous video, where we want to use our surface tension in X and our surface tension in Z to come up with a force due to surface tension in X and a force due to surface tension in Z. We're really only concerned with the force due to surface tension in Z because we have a free body diagram in Z, so we'll just focus in on that. To convert surface tension to a force, you need to multiply it by a distance. The distance that you multiply the surface tension by in this case is the distance of the line of contact between the free liquid surface in the capillary tube and the inner capillary tube wall, because that is the line of contact of the meniscus. And in this case, that distance is pi d, the circumference of the inner capillary tube wall. So we multiply our component of surface tension in Z by pi d, and that gives us cosine of psi times sigma pi d, and that is the magnitude of our Z component of surface tension force. So now we're just applying Newton's second law in Z with Z positive up, and there are a couple of notes here. One, when we look at our hydrostatic pressure distribution, which we can see on the previous page, the pressure at this point right here, which is not varying in x at all, our pressure along this line right here is P infinity plus rho g times the quantity big H minus little h, and we multiply that by A to get a force. But the pressure is just P infinity plus rho g times big H minus little h. You might be wondering how we're getting this big H minus little h. Remember in this case that h, little h, can be between negative infinity to infinity. It can be positive or negative. In the case where the liquid falls below the ambient free surface, little h is negative. So what we really want is the distance from this free ambient surface down to the bottom of this capillary tube. To get the distance from this free ambient surface down to the bottom of the capillary tube, we want h, capital H, big H, minus little h, because little h is negative. So minus a negative is a positive. So big H minus little h gives us the distance from the free ambient surface to the bottom of the capillary tube. So that's how we get that difference there. The second note is with the atmospheric pressure distribution. Again, you'll note that we're multiplying the atmospheric pressure by A, not the actual area of the meniscus, but the 2D projected area of the meniscus. That is a simplification, and we recognize that and explained that in the previous video, but you'll see that that allows our A here to equal our A here in our hydrostatic pressure distribution. So the next thing to note is this term right here. This is just the weight of the liquid in the capillary tube. We note that the area of the cylinder of the liquid in the capillary tube is approximately pi r squared, or pi times d over 2 squared. The height of the liquid in the capillary tube is that capital H, because that goes from the top of the liquid surface in the capillary tube to the bottom of the capillary tube. So that capital H is the height of the liquid in the capillary tube. So when we do pi r squared times H, this right here is the volume of liquid in the capillary tube. Rho is the density, so this gives us the mass of the liquid in the capillary tube. We multiply that by the magnitude of gravitational acceleration. This gives us the weight of the liquid in the capillary tube, and that is acting downwards with the negative sign. And we have our surface tension effect, which is just our surface tension in Z, which acts downwards as shown by the negative sign. And that is just our cosine psi sigma pi d, which we calculated as a magnitude up here. And then we sum all of those effects together and set them equal to 0 because we have a static problem. Now we're just going to do some algebraic simplifications. We see that our atmospheric pressure terms, our atmospheric force terms cancel out pretty immediately. And then our terms with capital H or big H cancel out, which is incredibly convenient. We saw this in the previous video as well, because when the terms with the big H, the capital H cancel out, we end up not needing to know very much about the construction of the capillary tube, because to know what capital H is, you kind of need to know the construction of the capillary tube, or where the capillary tube ends in the ambient liquid. We no longer need to know that. And then we break down our final algebraic terms here, and we can see that cosine of psi, we end up expressing as cosine of 180 degrees minus theta, and we will go into how to simplify that in a moment. Now we've skipped through some of the algebra. Feel free to pause the video and follow along as you wish, but as we skip through some of the algebra and we continue to simplify our Newton's second law analysis, we come up with this expression right here. Negative cosine of psi sigma pi d is equal to rho g times little h a. Now, what does this expression actually mean? The magnitude of the z component of surface tension is equal to the magnitude of the weight of the liquid that is evacuated below the free surface. So what does that mean? That means if we go to the first page here and you look at our diagram, which is this diagram right here, you can see that this red region is completely evacuated. There's no liquid. The liquid has completely retreated into this dome right here. Now, the weight of the liquid that would be in this evacuated region is equal to h, this height, little h, times A, which is this area right here, times rho times g. That is the weight of the liquid that would be in this region if it didn't evacuate and retreat into this dome. So this is, again, completely evacuated, but the weight of the liquid that would be in here is equal to A times H times rho times g, and that H is little h. Now, if we look at our current analysis, we have A times H times rho times g, where H is little h. That is the weight of the liquid that is evacuated below the free surface, the weight of the liquid that retreated into that dome. And that is equal to, in magnitude, the magnitude of the z component of surface tension, because if you take the magnitude of both sides, you get this expression right here. So the magnitude of the z component of surface tension is equal to the magnitude of the weight of the liquid evacuated beneath the free surface. Now that's very cool, because in the previous video, when the contact angle was less than 90, we found that the magnitude of the z component of surface tension was equal to the magnitude of the weight of the liquid that rises above the free surface, right? So in the previous video, when you have like something like water in a capillary tube and your contact angle is less than 90 degrees, you actually have the liquid in the capillary tube rise above the free ambient surface, and the weight of the liquid that rises above the free ambient surface, where this is the free ambient surface, the weight of that liquid is equal to the z component of surface tension, right, in magnitudes. In this case, it's inverted. When our contact angle is greater than 90 degrees, the weight of the liquid that is evacuated beneath the free ambient surface is equal to the magnitude of the z component of surface tension. So with that being said, we continue to simplify this expression right here. And the first thing you need to note is how we map cosine of psi to cosine of theta. Well, cosine of 180 degrees minus theta is equal to negative cosine of theta. So that's how we get from cosine of psi to cosine of theta. So negative cosine of psi sigma pi d is equal to positive cosine of theta sigma pi d. And then we just bring over the rho GHA to the other side of the equation. And that's how we get negative rho GHA plus cosine of theta sigma pi d is equal to 0. So now that we have cosine in terms of the contact angle, we can just do a bit more algebra from this expression right here and yield our final expression for little h, which is little h is equal to the quantity 4 times sigma times cosine theta over the quantity rho times g times d. Now this is the same exact expression we yielded for the case where the contact angle was less than 90 degrees. So now we've derived this equation twice, and we're gaining some confidence in its utility. So let's formalize it a bit. For one, this equation is called Jurin's law. It applies for contact angles between 0 and 180 degrees, and we can only say that it provides a first order estimate, and that's because we use some simplifying assumptions to derive it. For example, we assume that the area of the meniscus, the actual area of the meniscus, is approximately equal to the meniscus's 2D planar projected area. That's not quite correct, but it's close enough. However, as a result of that, we really should only call it a first order estimate. Now, that being said, it's still very useful, so let's continue with the formalization. So little h is equal to the displacement of the free liquid surface in the capillary tube from the ambient free liquid surface, and it is possible for little h to be positive or negative. So it's going to be positive when the liquid in the capillary tube rises above the free ambient surface, and little h is going to be negative when the liquid in the capillary tube falls below the free ambient surface. Little h is of typical units of meters. Sigma is the surface tension of the liquid in the capillary tube, typically greater than or equal to 0, and of units newtons per meter. Rho is the density of the liquid in the capillary tube, typically greater than 0, and of units kilograms per cubic meter. G is the magnitude of gravitational acceleration, typically greater than or equal to 0, and of units meters per second squared. And D is equal to the inner diameter of the capillary tube, typically greater than 0, has to be greater than 0, and of units meters. Now at this point, you can kind of see that there are pretty glaring similarities between the surface tension effects in a capillary tube, whether theta is greater than 90 or theta is less than 90. You could see that whether theta is less than 90 or theta is greater than 90, they're both governed by Jurin's law. And they're both governed by Jurin's law by the fact that little h can be positive or negative. And in concept, whether the liquid in the capillary tube is theta greater than 90 or theta less than 90, the behavior, the conceptual behavior is largely the same. So for example, if theta is greater than 90, so mercury in the capillary tube, for instance, the liquid in the capillary tube will retreat beneath the free ambient surface, and the weight of that evacuated liquid beneath the free ambient surface is equal to the z component of surface tension. And inversely, if theta is less than 90, so for example water in the capillary tube, the liquid will rise above the free ambient surface, and the weight of the liquid that rises above the free ambient surface is equal to the z component of surface tension. So there are some very fundamental differences, but also some very essential similarities. And in the next video, what we're going to do is briefly review how the pressure distribution kind of varies in the capillary tube as a function of theta and distance, and then kind of wrap up why some of this stuff is important. But for now, that should be it for this video. Thank you very, very much for watching. I really appreciate it, and I will see you next time.